Okay, this video is going to largely be a review of everything that we did last year with regards to center of mass. In the next video that I do, we're going to take a look at center of mass from a more sophisticated perspective in which we will use calculus to arrive at that location. Just as a reminder, center of mass is nothing more than the point which behaves as though all the mass is located at that point. It's as if the rest of the object doesn't exist. And what I mean by that is that, up to this point, when we've studied objects which are in motion, which are experiencing forces, the only thing that we ever worried about is though the object were just like a point. We didn't often have to consider that the object had any dimensions to it, giving it a volume. It was just this magical point in space, and we calculate how far that point moves. Now, you may not have thought of it that way, but that's effectively what we were doing. We didn't consider, was it the front of the car or the back of the car that was, moving from x equals 0 to x equals 10. We just assumed it was always the front or always the back or some middle location. Well, now we're identifying what that location is a bit more precisely. We call it the center of mass. Now, the center of mass is oftentimes just referred to as the CM, and that's what I've put in parentheses here. And then this leads us to another concept which is very helpful and very closely related to center of mass, and that is called center of gravity. Now, center of gravity is often referred to as CG, and the center of gravity is basically, it's the same point on an object. It's just now, instead of talking about the inertia of an object being located at that point, we're talking about the force of gravity is acting entirely on this point where all the inertia is located. So essentially, they're going to be the same thing. One is relating to mass, and the other is relating to weight. Now, you'll recall from last year that we had a couple properties for center of mass that are very useful in application purposes, recognizing where the center of mass is going to be located and things like that. So for these properties, and the first one is that if an object is free to rotate, so it's not fixed in any way so that it must move in a circle at a particular point. It must rotate around a particular point. So it's free to rotate. You throw the object into the air. When that object rotates, it will rotate around the center of mass. Okay, so for example, if you were to throw like a t-square, and basically a t-square looks like this, right? It just looks like a letter T. The center of mass for this t-square, we know that because of this long dimension here, that the center of mass is going to be located more towards the right, or somewhere towards the right, but it's definitely not on the left end and it's not on the right end. So the center of mass for this segment is going to be located in its middle, and the center of mass for this segment is going to be located in the middle. And so we see by symmetry that the center of mass is located somewhere along this line. Now, this left end is going to pull the center of mass, not literally pull it, but it's going to have the effect of shifting the center of mass a little bit to the left, and it's all going to be determined by how heavy each of these segments are. The center of mass for this t-square is going to be somewhere located in here. We don't know exactly where because we don't have all the details, but we know that it's going to be between these 2 points. All right, so that if you were to let this t-square rotate, it's going to rotate around this point when you fling it into the air. The second property for center of mass is this, that when the center of mass is supported, the object will be in rotational static equilibrium. Basically what that means is if you were to take a meter stick or this T-square, and if you were to pinch the end of it with your fingers while it's in this orientation, there's nothing underneath the center of mass holding it up. Okay, so there's no force pointing upwards at the location for the center of mass. And so basically what's going to happen is this thing is going to rotate around in that direction until the center of mass is supported. And when that happens, the T-square will now be in this orientation, and it's not going to be rotating. Okay, so that's all we mean by this statement, is that when the center of mass is supported, the object will be in rotational static equilibrium. Now, also take note that the force which is supporting it is going to be acting along this line right here. So the force that's supporting it, which is actually your fingers here, right? Because that's where you pinched it. The force that is supporting it doesn't actually have to be touching the center of mass. The only thing that matters is that it is supported along the line for which the center of mass is located. And remember, we said that it's located somewhere right around there. Another way to put it simply, even though it's a little early in our unit, we could say that there would be no gravitational torque. The last property we're going to look at is the fact that when an object is uniform and symmetric, that the center of mass will be located at the geometric center. Okay, now it's really important that we emphasize that it is both uniform in density throughout, which it does not have to be, and we'll look at examples like that. And then it must also be symmetric, or it must have those lines of symmetry. So examples of symmetry would be, say for example, we have a triangle, we have a line of symmetry here, so it is possible that we could use symmetry to help us locate the center of mass. And we'll be doing that whenever we look at this from a calculus perspective, in particular. If it's uniform density and symmetric, then, maybe we have something like a rectangle. We know that the center of mass would be located at its geometric center. But notice that when it comes to, say, a triangle, that we don't always have lines of symmetry. For example, if you look at a right triangle, we don't have any lines of symmetry here. And so the center of mass is located at a point that they call the centroid. And there, it's not hard. We can find the center of mass in both dimensions for that triangle, and maybe we'll do that in another video. But nonetheless, the center of mass here is not easy to find, which is what this number 3 is referring to. That's the whole point. When you have these simple objects, don't make more out of it than it has to be. You may be anxious to use calculus to find center of mass, but you don't really want to reinvent the wheel. In demonstrating our calculus techniques, we will use calculus to find the center of mass for things that are easy to identify. For example, if you have a long rod, where would the center of mass be located? We'll do that with calculus because we know it's halfway along the length of the rod. But then we'll get into the case where the rod is not a uniform density. And that's where you must use calculus to find it. So we'll demonstrate the principles of calculus using things which qualify under property number 3 here. But you're going to want to use property number 3 as much as possible, because there's just really no sense in trying to do it any other way. So again, we have we have this rectangle here. Maybe it's a sheet of plywood or something. We know that the geometric center is where the center of mass is going to be located. It's both symmetric and uniform in density. But what if you have something that's just a blob, something that looks like this? It might be uniform throughout. It might have a uniform density. In other words, it's a sheet of plywood cut into the blob, but it's not symmetric. And so now we can't easily find that center of mass. So one of the techniques that we can use to locate the center of mass for objects which are not uniform or necessarily symmetric, okay, one of those techniques is to just pick a point and let the object hang. So if I were to pick this point right here, then the object is going to swing down until it finds equilibrium, and it's no longer rotating, just like we had up here with our t-square. And then we know that somewhere along that line we're going to have the center of mass. And then what you'll do is you'll pick another point, and maybe the other point is going to be located right here. And once again, you would just let the whole thing rotate until it finds its point of equilibrium. And when it does, you know that somewhere along that line the center of mass is going to be located. So that when you take the intersection of those two lines, like for example, this line here may have done something like this. This line here may have done something like that. And then finally, we know that the center of mass would have to be located at the intersection of those two lines, which would be right there. Okay, so let's review very quickly how we find the center of mass when we have discrete particles. Now remember, a discrete particle is basically we have point masses. So I might have a mass located right here, and then a mass located right here. And so I just want to know where along this line is the center of mass located. So we'll just call this mass M1, and we'll call this mass M2. Now the location for center of mass, we use the equation XCM is equal to M1x1 plus M2x2 over M1 plus M2. And normally I just write this as M total because it's always going to be the total mass of the entire system of particles. Now this is for the x dimension. If these two particles had been oriented vertically, then I would write YCM is equal to M1y1 plus M2y2, etc. Now what do we have to consider before we can actually do this problem? And that is, we must consider where is the location for the origin. Because remember that x is a position in space. And so somewhere you must set x is equal to 0. So you could, in theory, say that x is equal to 0 here. You could say that x is equal to 0 here. And you could say that x is equal to 0 here. And all three of those points, quite frankly, are valid points, because coordinate systems are arbitrary. This is something that we learned back in kinematics. So you need to pick a point. Obviously, the most common location for x equals 0 is going to be at M1. So anytime you're solving a problem which involves center of mass, you just need to carefully consider what the origin is, whether you're comparing your answer to a friend's answer, or you're comparing your answer to the back of the book, or maybe just within the context of a problem, you haven't conceptualized what your answer is in relation to the whole problem. Because quite frankly, it's easy to set it up and you go through all the calculus and you're like, oh, that wasn't what I was expecting. And it turns out that, well, it wasn't what you were expecting. The answer is correct, but you need to be careful at what you're defining as x equals 0 within the context of your problem. Okay, so that's basically it. This is our equation for center of mass. So we're going to write XCM is equal to M1x1 plus M2x2 over M total. All right, now what happens if we want to find velocity? Okay, or VCM? Well, that's simple. we know that if we take the derivative of position with respect to time, that we end up with velocity. So here what we have is dx dt is going to be the same thing as VCM, which is equal to m1 dx1 dt plus m2 dx2 dt over m total. And what we end up with is VCM is equal to m1v1 plus m2v2 over m total. All right, and you should actually recognize this expression here as being conservation of momentum for a perfectly inelastic collision, which is the ones where the two objects stick together. So the two important equations are this one and this one. And remember that these are for adding up discrete particles. Now, the last thing that I want to discuss with you before I end this video and get into some examples is that when we're dealing with discrete particles, we do have a couple of situations come up. So we have 2D center of mass considerations, and basically all that means is that like if you have a piece of wire that's bent like this, then the center of mass is going to be shifted upwards because the location for the center of mass of this piece of wire is right here, and the location for the center of mass of this horizontal section of wire is right here. And so somewhere within this region outside of the object itself, somewhere there, we end up having the location for our center of mass, which actually turns out to be an important reminder for you, and that is that the center of mass does not have to physically lie within the object itself. And another great example of that is a donut. When you have a donut, the center of mass is going to be located right there at the center. Okay, so anyways, getting back to our piece of bent wire, basically what you have is a coordinate pair for each one of these. So this one's going to be 0 something, and then this one here is going to be something 0. And you'll just do your center of mass calculations for the x dimension and then for the y dimension, and you'll end up with an xcm is equal to, I'm just going to say 1, and then we have ycm, that's going to be equal to, say, 1. And so we know that if we go up 1 and then over 1, the center of mass for the whole piece of wire is going to be located right there.